Today we are going to talk about the Brayton cycle in relation to the first law of thermodynamics. We will briefly cover its application on gas turbine engines as well as ways to improve the efficiency. The Brayton cycle is a thermodynamic cycle that describes the operation of certain heat engines that have air and some other gas as their working fluid. The original Brayton engines used a piston compressor and a piston expander, but modern gas turbine engines and jet engines also follow the Brayton cycle. Although the cycle is usually run as an open system, it is conventionally assumed for the purpose of thermodynamic analysis that the exhaust gases are reused in intake, enabling analysis as a closed system.
A turbofan engine is the most modern variation of the basic gas turbine engine and has three components: a gas compressor, a combustion chamber, and an expansion turbine. The process is as follows. Ambient air is drawn into a compressor where it is compressed, ideally an isentropic process. The compressed air then runs through a mixing chamber where fuel is added. This is an isobaric process. The pressurized air and fuel mixture is then ignited in an expansion cylinder and energy is released, causing the heated air and combustion products to expand through an expansion turbine. Some of the work extracted by the turbine is used to drive the compressor through a crankshaft arrangement. This is the jet engine schematic with station numbers 0 through 3 and important parts of the engine labeled. From station 0 to 1, through the inlet and compressor, air is compressed, raising its temperature and pressure. In this process, the compressor performs work on the air. From station 1 to 2, in the combustor, fuel is introduced to the flow and combusted, adding heat to the system and increasing temperature in an isobaric process. From station 2 to 3, through the turbine and nozzle, the gas expands. During this process, the gas does work on the turbine, which is then transferred by the shaft to the compressor. It also does work in the nozzle, accelerating out of the engine to produce thrust. From station 3 to 0, after exiting the jet engine, the flow returns to free stream conditions, cooling down in a constant pressure process.
For the ideal Brayton cycle, we have to reject the heat for the cycle to work. Ideally, we would like to maximize work output of the engine. However, the heat loss decreases the efficiency of the engine. Therefore, we can talk about the methods how to improve the efficiency. One of the methods to improve the efficiency is the Brayton-Rankine combined cycle. The principle is that after completing its cycle in the first engine, which is Brayton cycle, the working fluid is still hot enough that a second subsequent heat engine can extract energy from the heat in the exhaust. Usually, the heat passes through the heat exchanger so that two engines can use the different working fluids. By generating power from the multi-streams of work, the overall efficiency of the system can be increased.